All right, let's talk about a subject that, let's be honest, can feel a little intimidating. General Organic Chemistry, or GOC. But what if we thought about it differently? What if it's not about endless memorization, but actually, it's a game? Let's get into it. One of the best teachers I ever heard of put it just like this. He said, "We call the GOC chapter the game of connectivity." And that right there, that's the key. We're not just studying a chapter today. We are learning how to play a game. So what's the point of this game? It's actually super simple. Every molecule, every single one, is a player. And they are all competing for one thing, one ultimate prize, to be as stable as possible. Every reaction you'll ever see is just a molecule trying to find its most stable, lowest energy form. If you get this one funda, you're already halfway to mastering organic chemistry. I'm serious.
Okay, so in any game, you've got to know the players, right? In our game, the players are these invisible forces called electron effects. These are the forces that control how electrons, who are the real MVPs here, move around inside a molecule. And that movement, well, that decides everything.
First up, we've got the inductive effect. Now you can think of this as a constant, low-key tug-of-war happening through the molecule's skeleton, the single bonds. So if you have a really electron-hungry atom, like chlorine, it's going to pull electrons towards itself. This creates a tiny ripple of positive charge down the chain. It's kind of like a domino effect that gets weaker and weaker the farther away you get. Next, we have a real heavyweight, the resonance effect. This is way more than just a subtle pull. With resonance, the electrons in double bonds, the pi electrons, aren't stuck between just two atoms. No way. They're shared across a whole group of atoms. It's like they're playing for the entire team. And this sharing, this delocalization, makes the whole molecule incredibly stable.
And here's something you absolutely have to remember. Those different drawings we make, the resonance structures, they're not real. They don't actually exist on their own. The real molecule is a kind of super stable average of all those possibilities, what we call a resonance hybrid. And that sharing is a massive win for stability. Our third player is hyperconjugation. Some people even call it no-bond resonance. I like to think of this as a helpful teammate. What happens here is that electrons from a nearby single bond will kind of lean over and help stabilize an atom that's short on electrons, an atom that has an empty slot or p orbital. It's just another smart way molecules spread out charge and become more stable.
So, there are our players, the inductive effect, resonance, and hyperconjugation. But what happens when they're all in the same molecule? What happens when they start competing? Who wins? To figure that out, we need the official rulebook.
And this is the big question, isn't it? In any complex molecule, you could have all these effects pushing and pulling electrons in different directions. So how on earth do you decide which one gets the final say? Which one is the most powerful? Well, here it is. This is the ultimate cheat sheet for stability. This is the order of dominance. At the very top, the undisputed king is something called aromaticity. After that comes resonance, then hyperconjugation. And last and kind of least is the inductive effect. Just remember the acronym RHI. A-R-H-I. This simple hierarchy is the key. It's the secret to solving pretty much any stability question you'll ever face.
Now we have to spend a moment on the absolute champion at the top of our ARHI list, aromaticity. This isn't just another effect on the list, it's more like a superpower. It gives a molecule a level of stability that's just off the charts.
But like any superpower, it has very strict rules. The molecule has to be a flat ring, it needs a continuous loop of pi electrons, and it has to have a very specific magic number of those electrons. The most famous example, of course, is benzene. It follows all the rules, which makes it unbelievably stable and the clear number one in our game.
All right, that's enough theory for now. The best way to actually learn the rules is to play the game, right? So let's jump into the championship round and put our ARHI rulebook to the test.
Okay, here we go. A classic organic chemistry problem. We've got 3 different carbocations here. The question is simple. Which one is the most stable? Let's break it down with our HARI rulebook.
Okay, let's apply the rules. A for aromaticity? Nope, none of these are aromatic. R for resonance? Nope, no resonance here either. So that brings us down to H, hyperconjugation. And for that, all we have to do is count the hydrogens on the carbons right next to that positive charge, the alpha hydrogens. The tertiary one has 9, the secondary has 6, and the primary has only 3.
And just like that, the answer becomes crystal clear. With 9 alpha hydrogens giving it the most possible help from hyperconjugation, the tertiary carbocation is the winner. It is the most stable. See? The rules work. It's that simple.
So, we've learned about the players, we've learned the rules of this molecular game, but let's ask the most important question. Why does any of this actually matter once you leave the classroom?
And you've got to understand, this is not just theory. This game of connectivity is being played out all around us, and even inside of us, every single second of every day. These exact same rules are what determine how life-saving medicines work, how strong plastics and polymers can be, and even how the DNA in our cells holds itself together. When you understand stability, you understand the blueprint of the entire material world.
So, we've learned the rules that molecules desperately try to follow to find stability. But now for the really cool part. What happens when we, as chemists and scientists, learn how to bend those rules, or even how to break them to build something completely new? Well, that is where the real magic of organic chemistry truly begins. Thanks so much for joining me.